Hello. In this video, we will study the uniform convergence, which is maybe, as I said at the end of the last video, the worst of the worst. The most difficult concept, maybe the most difficult mathematical concept you need to understand in this course. As usual, I will try as easy as possible. I will explain as easy as possible. Hope it works and think about. Let's start. So the uniform convergence, to define the uniform convergence, we will consider a sequence of functions now. So think this is an example. Define fn. It's a sequence of functions. So f is a function and it depends on n, and it is 0 or 1 over n times x. So and then, as you can see, as n goes to infinity, the function automatically goes to 0 because the denominator goes to the infinity. Then, obviously, fn converges to 0. So, this is true. So, we say that the limit of the function is 0. So obvious. There is no doubt about, no question about this. But we call this pointwise convergence. It is a pointwise convergence concept because we don't consider x. So no matter what x is, it converges to 0 as n increases. But now our question here is, let me show you this first. So now, our final question is, we would like to have a sequence of function and at the same time a sequence of the argument x. And functions converge to something and x converges to something, and when you combine them, the combination of them converges to the natural limit or not. The answer is not that easy, so let's go back to this point. So we will consider xn converging to 0. So we now not only fn changes, but also x changes as n increases. So as an example, we will consider xn equals to 1 over n. In this case, what's interesting here is we said as n goes to infinity, the function converges to 0. But if you consider this, if you plug this into the functional form, then x is 1 over n, so the denominator is 1. Therefore, fn of xn is always 1 for any n. So in that case, it does not converge to 0 at all. So the limit is now different. So the limit will be different if you change the sequence in xn. So if the sequence xn is converging to 0, slower than 1 over n, then the function will converge correctly to 0. But if it's converging to 0 faster than 1 over n, then it will diverge to the infinity. So the result, what we wanted to do here is this, but this answer is not easy. The answer is not easy, and especially, as you can see, it depends on how fast xn changes. How fast xn changes and how fast fn changes. So we have to restrict them, and the idea here is, and the problem here is the different convergence rate of fn at different points. I have a graph. Let me show you the graph. So this is the function fn that for 1, 2, 3, 4, 5. So the blue on top is f1 and f2, f3, f4, f5. As you can see, it is converging to 0. It goes down as n increases. But however, if you move, however, it is very slow at this point, right? So for example, think about 2 points. Suppose that your x n is here. I will. So this point is Fn. Point is on Fn. But now think about. Oops. Excuse me. What happens? Oops. Excuse me. So this point, so the original point was on Fn and F1, and suppose that the second point is on F5. Then what you see here is as n increases, the function as n increases from 1 to 5, this point moved from here, which is on F1, to here, which is on F5. And also x is converging to 0, but so even if it has been moved from F1 to F5, but after the move, the point is now further away from 0. So previously at this point it was 5, but it is now near 20. So the problem here is the convergence rate at this point is too slow. So convergence rate is faster as you move away from 0, but as you move towards 0, the convergence rate is super slow. Like as you can see, still it is near 20. So 0.01 is still 20 even if n is 5. So that's the problem why if you move this direction, you cannot guarantee you are moving to 0. You may be moving away from 0, like this. So like this. So I wish I had a blackboard, but so the point here is the convergence rate is slow, and then how can we do? We have to restrict the difference in the convergence rate across different points. So we define a more restrictive convergence of a sequence of functions. We define this. So supremum over x, supremum of the difference between f and f0 converges to 0. So the supremum captures the maximum difference between the limit and Fn. So there is a so at some point it converges quickly and at some point it converges slower. But what it says here is the supremum is capturing where the maximum is the difference is the maximum. So it requires that even at the point which has the slowest convergence rate, the difference must converge to 0. And in our previous example, the supremum, the maximum of the difference is obtained near 0. So the difference between the limit is 0. So the difference between the 0 and a point, the function, is infinity as you move towards 0. Near 0, it will be infinity. Therefore, you can show that it does not converge uniformly. This function does not converge uniformly according to this definition. So for this definition to be true, you have to think like that. So if there is a limit function, then you must have a band around the limit, and the band must shrink. The bandage must shrink toward the limit function so that all the functions lie within this band. So when n equals to 1, like the functions lie within this point, and as n increases, the variation of the functions move toward a point, and in the end they get to one function that is the limit according to the uniform convergence. So then now what we wanted is this. Suppose that the sequence of functions converges uniformly to a limit f0. And second, x and the argument converges to a point x0. And then finally, f0 is continuous. So continuous at the point, at the limit. And then you can say that f and xn, the combination, so two sequences combined, the sequence of functions and the sequence of numbers combined, and generates another sequence, and the composite sequence converges to the natural limit, so the intuitive limit, that which combines the limit of the functions and the limit of the numbers. The intuition here is so we, as I said, it's a composite sequence. So break down the sequence into two terms. So fn minus f0, which fixes x, but which looks at the difference between fn and f0. And the second difference is in x0 and xn and x0. So the first term captures sequence of functions, and the second term captures the sequence of x. And then the first one converges to 0 by this assumption, uniform convergence. No matter what x is, it converges to 0, because every point moves together. Every point moves at a certain rate, so there is no one left behind. There is no one who is too slow to match the other points. So the first one converges to 0 by the assumption, and second one also converges to 0 by the continuity and convergence of xn. So the second and third assumptions imply the second term converges to 0. So so that is what we need later to have, like, so previously, as you have seen, like this, it is an extension of this idea, is an extension of the continuous mapping theorem. So continuous mapping theorem assumes that the function does not change, but later we are going to see the function also may depend on n. So then we need to generalize the continuous mapping theorem to another more general theorem, and that theorem will require the uniform convergence. So then in the end we are going to get the natural limit, which is simple. The conclusion is always simple. The conclusion is always intuitive. The process to the point is the boring part. So let's call it a lecture. We are going to extend the theories a little more in the next lecture, and then we will directly start the M estimation theory. So the next lecture will be more difficult. Thank you for watching. See you later.